Provincial thing system.就准备查了，看没给我上网那个啊，我背过没做好久。像汽车的本来准备搞个电这样，那现在死了看。
Okay, let's get started. Anybody have any questions before we get started? Anything? We'll just jump straight into stuff. Maybe just to remind everyone that the homework's due in a week from tomorrow, because next week is Thanksgiving, so it's due the day before we go off on Thanksgiving break. And then just a reminder to be thinking about your final projects, what you're doing. Planning to give to everyone just at least brief feedback on their proposals this week. Not really graded per se, but we'll just give feedback. But also if you have questions about your proposal and idea, or you want to talk about it in office hours or after class, feel free to discuss your, a few of you've already discussed your project ideas with us, but if you have, questions or things you're thinking about, or places you need help, maybe looking stuff up, don't be afraid to come talk to us about your projects. Okay, I think that's everything I can think of on in terms of logistics, but any questions? All right, so we had just begun talking about Fisher information last week. And let's pick back up there. And we had just gotten to the point where we defined what the definition of Fisher information, but we didn't really explain where that equation comes from and why it's useful as a reminder metric. But let me remind everyone that our setting is we're starting with a random variable which has a probability distribution. We're modeling with a PDF or PMF, depending if it's, remember, probability density function. Or if it's a discrete variable, you can say a probability mass function. Let me say with PDF or PMF given by P of X and some parameters, which we'll just say are theta. Just a note here, I'm being very general here. So X, like I said, could be a discrete random variable. It could be a continuous random variable. It could be a vector, multivariate random variable. It could be an image, time series, text. It could be whatever kind of random variable you want. And likewise, theta can be just a single parameter. We'll do the Bernoulli distribution where theta is the probability 0 to 1 of a discrete coin flip, if you will. But it could also be a vector of random, vector of parameters, like even the very simple Gaussian case, you've got a mean mu and a variance sigma squared. And so you would lump them together into a 2-vector and call that theta. So this is very general, very broad. And a last thing I'll mention is we talked about like a variational autoencoder or some other generative model. Amon's going to be talking about diffusion models after this module we're in currently. They're kind of like the hot topic in generative AI. And you can lump those together here as well. Any kind of neural network model. The parameters are the weights of the neural network or convolutional network, whichever the network you got there. So yeah, so anyway, the point is that this is very general. Anytime you have a probabilistic model of data and you have parameters of that probability distribution. Okay, in this setting, we have, this is, if you give me some fixed data, right? Say a fixed point X, take the data point I've observed, okay? Then we would call this the likelihood of our model. Given the data point, the likelihood function, L of theta, you think of the function of theta, because we're going to think of that observed data point as a constant now, because we've seen it. It's not random anymore, because we've seen it. This would just be taking, sorry, this is the likelihood. Hang on a second. The likelihood, we typically use the capital L notation, in statistics at least. In routine learning, you would typically not do that because you have the log function. Anyway, but then the log likelihood, so little l is just to take the log of this thing, natural log of your likelihood. And again, I'm thinking of it as a function of theta now, and the f is the observed point. And of course, with most data analysis problems, I don't try to learn the parameters with just one data point. I would do this over a product of the likelihoods of multiple data points. So if I have capital N samples or sample of capital N observations, I just take the product of all of their individual likelihoods. And that product, when I take the natural log, of course, there comes the sum on the outside. So our likelihood, log likelihood is typically a sum over lots of individuals, data's points, likelihoods, log likelihoods. Yeah.
What is the difference between that big L and small L? Because they're both likely, right? So,
Well, this is the likelihood, and now just take the natural log of it. That's the only difference.
okay.
Yeah, take the log, LN.
And the P there means like given the theta, what is the probability of observing xi?
Okay, so we have to be careful if it's a probability mass function. It's the probability of that data point, yes, but if it's discrete, you have finite outcomes or discrete outcomes rather. If it's a continuous random variable like in a Gaussian, this is a density, and a density is not a probability. It's a thing you have to integrate to get probability over an interval. So yeah, so it's the likelihood is, yeah, either a mass function if it's a discrete random variable, or as is most often the case in things we're dealing with, it's going to be more usually a PDF. But yeah, that makes sense. Okay. So yeah, so I'll give a couple of concrete examples, really just the Bernoulli and the Gaussian, like kind of your most classic statistical probability distributions that you do in like intro probability. We'll go through those examples in a minute. But you can plug in like probability density that comes out of a variational autoencoder also. You can't write it down on paper, but you can at least talk about this expression at least. Okay. Right. And then the next thing, okay, so yeah, so this is the likely, right in the words, likelihood, log likelihood. And the last thing we talked about in this sequence of things is taking the derivative of the likelihood, or log likelihood rather, with respect to theta. So if I take 3L theta, and again, I'm going to be a little bit vague about what this derivative is. If theta is just a single parameter, so obviously, by the way, theta has to be continuous for this next step to make sense. So a continuous parameter, which all the examples we've had so far fall in that case. Even the discrete random variable like Bernoulli, the probability of zero is this continuous number from 0 to 1. So even a discrete random variable can have continuous parameters, so that it's that makes sense. And the Gaussian mean and variance are continuous, so that all makes sense. But anyway, this derivative might mean just your usual derivative of a function of one parameter. But if this is a vector, a multivariate likelihood, let's say, multiple parameters, this would mean like the gradient. Okay, this would be like grad L, where the grad is with, again, gradient is with respect to the theta vector. Okay, so either way, we can write down the derivative of the log likelihood, and this is something we call the score function. I'll just make a preview, if you will, to Mons. I really don't know how you're going to present diffusion model, but you're going to talk about score-based scored functions. Okay, so score functions are very, again, very useful in generative models and diffusion models. As you're going to see in a Mons lecture, you'll see a connection there that the score function is something we can use to train a generative model. So if this P of X theta is a generative model, I want to be able to pull samples from P of X, because you think about generative modeling, I'm trying to generate fake data. That's like sampling from a probability distribution that I've learned with a neural network. And so you learn the weights of your neural network, those are the theta, and then I can take that neural network and sample from it. This is what, you know, all the kind of cutting edge generative AI models are doing, like at least image generative models are doing these diffusion models, which are based off of this principle of the score function and learning through the score function. We're not going to do that in today's lecture, but it's just a preview to later. So this is, you know, I'm not going to simplify the derivative, but you can just imagine for now, I'm just going to take it on the inside here. Obviously, we all know how to take the derivative of log. We'll do it here in a minute. But again, the key thing is to remember that xi, the actual data, are constants, and the theta is the parameter we're taking derivatives over. Okay. So given the score function now, we can define the Fisher information. So the Fisher information is going to be just, it's usually denoted with a script capital I, or theta. It's equal to the variance of its score function. And this, at the moment, doesn't make any sense to anyone, hopefully, or maybe not hopefully, but I assume this doesn't make any sense to anyone. This is very opaque. Why is this a quantity we care about? A very important thing to note here is that this variance, right? Variance is a property of random variables, of this probability distributions. The random variable we're talking about, I'll just put as a subscript here, is the x. So we need a random variable to take the variance of this quantity. This d theta dl is or dl d theta is a thing we can evaluate. And let's just think about you know, it's a number, right? If theta is a nice single parameter, and we evaluate it at a particular value of a parameter theta, and then we can vary randomly the x, and then we take the variance of this quantity as a random variable itself. Okay, so that's the idea. So we're going to do some computations to see what this looks like, and again, the thing I will point out that we mentioned, the whole point is for the purposes of geometry of machine learning and so forth. The reason we're doing all of this is that we can take the Fisher information and use it as a Riemannian metric, and it's a Riemannian metric in theta, and so your parameters of your models now become a Riemannian manifold, and distances between different distributions in that parameter space are geodesic distances. Okay, and this is a let's say natural Riemannian metric, more natural than just saying, oh, theta is a Euclidean value, and I just take Euclidean distances in theta. So, for instance, if you thought about, I've got two Gaussian distributions. I don't know how close are they, and you're going to do this in the homework if you do problem number 2 or whichever it is. You know, you could just say, well, what's the difference in the means and the difference in the variances, and then just add them up, right? Or some squares, add them up and say that's the Euclidean distance between these two Gaussian distributions. but it actually makes more sense to put this into a Riemannian geometry and measure distances due to geodesics there. And we're gonna kind of, that's what we're gonna kind of look at here. Okay. Right. So, so the first thing, any questions about the setup here at least? Okay, so the first thing we're going to do is break down this variance definition of Fisher information and show its you can write it a little bit differently without the variance part. You can just look at the score function itself. So the first thing we'll do is a little expectation calculation exercise. What is the expected value of the score function? So again, that's my score function. Again, it's a random variable x. I can take the expectation of this score function. Okay, let me. By the way, I'm just going to leave out the sum over multiple data points because it's all just. All these things like expectations, linear, so if I had a sum of score functions, the sum would come outside the expectation. So it suffices just to look at one data point score function for the purposes of the calculation here. I'm going to, for the moment, work it out for continuous random variable x, but the same calculation works for discrete random variables x. You just change integrals into sums and you're good to go. And the same flow works the same way. Okay, so let's do this. The expected value of a random variable, remember, is the integral over the thing inside the square brackets here. So that's the score function. Times the PDF and integrated over the values of x. And this range, I'm going to just leave out. Depends on the range of what x values are, but you can put in the range. Okay. And if I look at, now I'm going to do this derivative of log p, right, with respect to theta. Derivative of log is 1 over p. And then the chain rule is going to be the derivative of p, right? So I get dp d theta. Okay, that's the chain rule term, and then 1 over p of theta. P. I should maybe write it out from the top also, since I'm right out the bottom here. But yeah, that's that. Oops, sorry, I had that square bracket. Sorry. Okay, so that's that derivative of the log likelihood is this thing here. And then this stays around here. I've got this and that canceling, right? So this becomes the integral of dv theta of my likelihood out the log, like so. Okay. And with assumptions about the differentiability of things, I can pull this derivative outside the integral because the integral is over x, the derivative is over theta. And that looks like so. Okay, just swapping integration derivative. I mean, I should say, I'm assuming the bounds of my probability distribution don't depend on theta. That's what we're really doing here. So if they don't, I can pull this derivative outside the integral. And now notice the integral of a probability density function over the full range of x is what? 1. Okay, someone's awake. Good. So we're doing the derivative of a constant 1, and that's of course 0. Okay, so what we've shown is that the expected value of the score function is 0. Another way of saying, remember, expected value is just the average value. The average of the score function over the whole probability distribution is 0. And that's always the case, no matter what the probability distribution is, whatever the random variable is, again, assuming you're working with parameters that don't change the bounds of integration of your probability distribution. Okay. Any questions about those kind of steps? Yeah.
How do we derive from the one that's above to that one?
This one to this one?
Yeah, because the one inside the parentheses.
Yeah, so this is L of theta is little side note is log of P. Sorry. Yeah, sorry, yeah, it is log of P, and I'm taking, I write it out, I'm not too lazy here. So log of P x theta. And so derivative of natural log is 1 over, right? So that's where I get the 1 over P of x theta. And then there's a chain rule. So then I have to take the derivative of P of x theta. And that's what I'm writing up here, kind of a little bit lazy getting the x theta there, but yeah. So just this is the derivative of log P that we're writing. Okay. Okay, so now coming back to variance. Again, this is kind of testing people's brain cells. If you took intro probability, talking about expected values and variances of random variables. So now let's write the Fisher information as the variance of the score function. Remember that variance can be written as the expected value of the thing you're taking the variance of squared. So this thing squared minus the expected value of the thing in brackets and squared on the outside. Okay, so it's like if we're just doing a random variable, like E of x squared minus expected value of x squared on the outside, right? But we're not doing x, we're doing the score functions, the same we're taking variance of. Okay, and we just saw that this term, the expected value of the score function, before you take the square, is 0. So this second term goes away. And what we can see is that the Fisher information, if I don't want to think of variances, I can kind of simplify this a little bit in terms of the score function, is just square the score function and then take the expected value. And the camera has lost me. Okay. Any questions about that step? Is pretty straightforward. Hopefully we saw that piece there. Okay. So Fisher information, I can write as the variance of the score function. I can also write it as the square of the expected value of the square of the score function. And then one last thing I want to do is write it one more way to be important. All this is important when we want to sort of understand what exactly the Fisher information gives us. So now let's look at the second derivative of the score function. And again, we're going to be taking the second derivative of, remember, just log P of x. Sorry, this is the second derivative of the log likelihood, not second derivative of the score function. This is kind of the first derivative of the score function. Score function's already got a derivative in it. But yeah, what do I get here? You can you get second derivative of P and divide it by P minus the derivative of P over P squared. Okay. And what I want to do now is take the expected value of this whole thing So now the expected value of the second derivative of the log likelihood. The first thing I'll say here is if we look at this first term, you can hopefully see that this also will go to 0. That's it, this whole term is 0. Why is that? Same trick as we did over here with the first derivative. If this were a second derivative, take the expected value, the p's cancel out, and I've got the second derivative of p. I can pull that out of the integral, and I'm still taking a second derivative of a constant. Okay, so just you can kind of maybe verify for yourself that that is the same trick I did over there, just with the second derivative instead of a first derivative. So what I've got, I'm going to actually, well, yeah, let me put a, yeah, let's do it this way. Plus expected value of squared. One second, I'm getting mixed up for a second here somehow, which happens sometimes. Take the expected value of not getting what I should be getting here. Oh. Oh, yeah, no, okay. Okay, fine. Sorry. Yeah, what I want to do now is rewrite this. I was somehow thinking this was already the score function at the top. Yeah, this is just sorry for the long awkward pause. This is this, if you notice, is just the derivative of L of theta here, because it's the derivative of log, gives me same thing I had over here, dp over p, right? And this is dp over p, but it's squared. So this is the expected value of the score function squared. With a minus sign. Sorry, let me get this minus sign in the right place. So there's a minus sign here. Okay, everybody happy with that? After my long, I'll call it brain freeze. Did that make sense? This is dp over p, which we had just done over here, is derivative of the little l is dp over p. Okay, so this is derivative of L, which is the score function, and it's squared. And that, of course, if I didn't have the minus sign, is what we have as the Fisher information. So we see that the second derivative let me swap the minus signs here. Okay, the second derivative, the negative second expected value of the second derivative is also the Fisher information. Okay, so I've got kind of three ways of writing the Fisher information. I can write it as the variance of the score function. I can write it as the expected value of the square of the score function, or I can write it as the negative expected value of the second derivative of the score function. So three different ways of thinking about the Fisher information. Okay. So with that little math exercise out of the way, now let's try to look at a concrete example and see what exactly is the Fisher information telling us in a simple case. Let's do a Bernoulli random variable. So remember, Bernoulli random variable is your standard 0, 1 discrete random variable, coin flip, heads, tails, bits, if you will. So I'm going to say my random variable x is distributed as a Bernoulli with probability theta. That's the parameter. It's the probability of a 1, 0 to 1 value. Let me just write that here. Theta is the probability of x equal to 1, and that means, since there's only one other value, that 1 minus theta is the probability that x is equal to 0. Okay, so this is again my probability 101. The first day you talked about random variables, you talked about Bernoulli's. Okay, so let's work out what is the Fisher information for this very simple random variable. First let's write down what is the likelihood. In case people haven't seen this or maybe have forgotten this, it's more likely. There's a little trick here. I can write down my probability like so, or this is now a probability mass function. Sorry, I think that's not pulling together too much. So just really quickly to refresh everyone's memory, x is 0, 1, right? So if I say probability x equals 1, this exponent will be 0 and it cancels out that term and I get theta to the 1. That's probably if x equals 1, and then I flip it, I put x equal to 0. This gets canceled out, this exponent becomes a 1, and I get 1 minus theta is the probability. Okay, so you can think of these exponents as kind of like selectors of this term or that term if it's 1 or 0. Okay, so that's the PMF, probability mass function for Bernoulli. And now I'm ready for writing down the log likelihood. Is just taking the log of this thing, the log of theta to the x, 1 minus theta to the 1 minus x. That's the log of this whole thing. I should be clear. Okay. And I'm just going to do one step here. Using all my usual rules of taking logs of things. Okay, so this is my log likelihood for Bernoulli. And by the way, you can do binomial. If you have like a run of Bernoulli's, obviously it's just a product or sum over these things and so forth. Okay. Any questions so far? Okay, now let's take the first derivative. of this log likelihood. So now this is my store function, is the derivative of L theta. With respect now to theta, let's be clear. So I'm just going to have derivative of a log is 1 over, so that's just x over theta plus there's going to be a chain rule minus sign there. I'm going to get a negative 1 minus x over 1 minus theta. Okay. What I can do is just take the expected value of this squared, square this and take the expected value of it. Let's see, in my notes, I think I do this. Okay, I'm going to do the second derivative version. So now let's do the Fisher information as just remember the expected value is a minus sign of the second derivative of the score, or sorry, of the log likelihood. Okay, so I just need one more derivative here, and then take the expected value. So how does that look? This is going to be 1 over x goes to 1 over theta, I should say, goes over to minus 1 over theta squared. Right, and then this term 1 over 1 minus theta squared is going to be, again, chain rule, with a minus sign there, and 1 minus theta squared here. Okay, and then you take the expected value of x. This is all linear expected value, right? So I can take expected value of this term, expected value of this term. These are constants with respect to expected values, and really take the expected value of x, which who can tell me what the expected value of a Bernoulli is? You might.
Square of no.
So I've got a Bernoulli random variable with probability theta. The theta matters here. What's the expected value of x?
1 by theta.
1, you mean 1 over theta? Is that the? Oh, you're in ballpark, not quite. So expected value of x. Oh, sorry, you're doing the whole term. Are you doing this whole term or are you doing just x? I'm asking, yeah, so expected value of x. Let's start with and so we should do a quick again, because everyone's forgotten. I mean, I don't blame anyone because it's been a while probably since anyone took probability. So I would be the same. So let's just do a little side note. If I had this Bernoulli random variable up here and take the expected value of theta, it's going to be 1 with probability theta. It's going to be 0 with probability 1 minus theta. It's not quite 1 over theta. It does depend on theta. Every time I get a 1, I'm going to get, right, like theta per proportion of the time I'm going to get a 1. Yeah, exactly, it's theta. Okay, so let's I got time here to go back to your maybe undergrad probability. So remember the expected value of a random variable is going to look like the sum of all the possible outcomes. And we've only got 2 outcomes. I'm going to write this as A, is the outcome is either 0 or 1. It's going to be the value of the outcome times the probability that X equals that outcome. Okay, and so I've got A is 0 times the probability of 0. The probability of 0 really doesn't matter, but it's 1 minus theta. And then I've got A is 1 times the probability of that, which is theta. Okay, so that becomes theta. Okay. Think about if I flip a coin, right? That has like a biased coin that comes up theta % of the time, proportion of the time it comes up heads, and I just take the number of heads divide by the total number of flips I did, on average, the proportion, it's me averaging zeros and ones, I'm gonna get whatever that probability was. Okay, so yeah, so that's the answer. So expected value of x, it's just be theta, so I get theta over theta squared here. That's now when I combine that's gonna be 1 over theta. I'm negating the negation. And same thing here, I'm gonna get 1 minus theta in the top, which is gonna cancel one of these. And I'm gonna negate the negation again and get 1 over theta over 1 over theta squared, which is 1 over 1 minus theta. Okay, so that's the Fisher information. I can collect these two terms. If I multiply by 1 minus theta over 1 minus theta here and theta over theta here, you can collect these terms and it becomes 1 over theta times 1 minus theta, like so. Okay, oops, sorry about the camera. All right, so that is our first example of sort of the simplest random variable you can do, probability distribution. The Fisher information of the Bernoulli is 1 over theta minus, sorry, 1 over theta times 1 minus theta. Okay, yeah.
So like, I don't know how do we do this, but like, how do we interpret this?
Exactly. That's question, or sorry, point number 2 that we're going to do now. Okay, but any questions about the calculation? I'm going to do the understanding of this here in a minute. Any questions about the how it got there? Okay, so let's plot the Fisher information. I'm going to write the interval 0 to 1 here on the x-axis. This is really, I should say, the theta axis. And then the vertical axis, I'm going to draw the function I theta, which is 1 over theta 1 minus theta. Okay. As theta goes to 0, this denominator goes to 0. First of all, notice theta is between 0 and 1, so this is always a positive value. So yeah, but as theta goes to 0, this goes to infinity. As theta goes to 1, 1 minus theta goes to 0, so this also becomes infinity, positive infinity. Okay, so we know that as you approach the edges of your interval, it is kind of asymptotically goes to infinity, and it kind of goes down here and then back up there. What is the basement floor of this thing here? You can hopefully convince yourself that this term, 1 over this term, theta 1 minus theta, it maxes out at 0.5. Theta equals 0.5. So 0.5 times 0.5, which is 0.25. So the basement, the bottom of this, is at 0.5. You should also be able to convince yourself this is symmetric, despite my poor drawing. This is symmetric. If I mirrored it about 0.5, I'd get the same curve. Okay, so just to give you a sense of what this looks like, yeah, the basement, it bottoms out is at 0.25 is the minimum Fisher information. Or sorry, 1 over 0.2. 1 over 0.25, which is 4. Okay. So that's what the curve looks like. At the middle, it's at 4, and it goes off to infinity, kind of this kind of curve like so. All right, and what does this tell us? So what, first of all, you may have noticed Fisher information has some dude's name in it, and it has the word information in it, right? That's what this capital I is. We're thinking of it as information. So what does that mean? The way to intuitively think about it is it's telling us how much information do we have about a random variable's outcomes depending on the parameter. Okay, so if I gave you a particular parameter theta, how much information will we have about the outcomes we might expect? So observe the following. If I have a parameter equal to 0, I always get 0. You never get 1, right? I have infinite information about the value I will get. It's always going to be 0. So I don't need To know anything else, I've got full information. If same thing on the other end, I'll always get ones if I have theta equal to 1, so I have infinite information. If theta equals 0.5, it's 50-50, and I have minimal information about my random variable outcomes. But the closer I get to the boundaries, the more likely I'm going to be one particular value. So if I had to predict, I would just predict that value and I'd be more right than I would be wrong. And so I have more and more information. Okay. The next thing to point out here is I can use this now, like we said, as a Riemannian metric. I of theta is the Riemannian metric for my theta space. So my theta space is just a unit interval now. But the point is that I don't want to just move at constant speed. What I want to do is I want to remember the I can call this now G of theta if we use the notation we had before of a Riemannian metric. This is now a 1-by-1 matrix, right? So it's a positive definite matrix because it's just a positive number. It's a positive definite matrix. We have a 1-by-1 matrix. Okay. And what is it telling me? It tells me that if I have a theta value, I'm on a point in this manifold somewhere, and I want to move in a tangent direction from that theta value, what is the speed at which I'm moving? Okay, so I have this velocity v, and remember now the norm of v in terms of Riemannian geometry is going to be the square root of the inner product of v with itself, which if I'm in this coordinate system, which I am, I'm in this theta coordinate system, g of theta is in that set of coordinates, that's going to look like v transpose g of theta v. Of course, v is a 1-by-1 vector here, so v transpose v is kind of really a multivariate thing. I'd have a matrix, and v would be a vector. So in the case of Bernoulli, what is it saying is v is just a number. I'm just taking g of theta times v squared. Okay. And so what this says is if in terms of Euclidean theta length v, I kept v constant. If I move closer and closer to the boundary, I really need to scale the speed up by g of theta. And so keeping it constant in Euclidean sense would be increasing the speed. Now, if I want to move in a geodesic, I need to stay constant in terms of this speed. Okay. And that means v needs to shrink at a rate of 1 over g of theta. So it needs to shrink 1 over this, which is theta times 1 minus theta to stay constant speed. It's actually moving the length of v in terms of Euclidean theta is actually going to have to be theta times 1 minus theta ish, or square root of that speed to kind of stay constant to be a geodesic. So it moves and it slows down and never gets to the boundary. These geodesics are really going off to infinity, but it's again asymptotically approaching the edges, but never actually hitting them. So that's what geodesics under this Fisher formation look like. Is that a question or whatever?
Yeah, that's pretty much answer. It's essentially access proportional.
Yeah.
Right.
Yeah, exactly. Right.
In what, like, does it apply to sphere as well? The motion on a sphere specifically?
So let's see. If I had, so this applies to parameters of the distribution. And so you could conceivably talk about a parameterized distribution on the sphere, and then have a Riemannian metric on the sphere for that parameter. So there are parameterized distributions on the sphere, like on these kind of type distributions, Fisher distribution kind of things that you can have parameters for. So you could conceivably do this, yes, for a sphere. but they're usually like a Gaussian. They have at least a like a Watson, there's a whole bunch of them, but there's usually a central location on the sphere is like the mean parameter, and then there's a dispersion, like kind of like variance parameter. So you usually have like a multivariate set of parameters there. And I believe if you kept the variance dispersion parameter fixed, that everything's symmetric, and so the metric you would get would basically just be the usual sphere metric for the centrality parameter. I believe, I don't know that for a fact.
Where exactly do we apply this? What do we need this velocity for?
Yeah, so we're gonna do a so this is, I don't know that this is super useful, the Bernoulli, but it's an example that we can write down the equation and we can draw it on the board and see what it does.
Okay,
But yeah, so where we use this one, I don't know that it's super useful,
like
although I will actually, there's one place that's useful. Sorry, let me not dismiss it completely. So in terms of the geometry, I don't know that people use this as a Riemannian metric on just the unit interval. I don't know how useful that is, but in terms of Fisher information more broadly, it's not just used as a Riemannian metric, it's used more broadly for other things. There's a couple of other things people use this for, and let me just mention one so that you have another sort of application. In Bayesian analysis or Bayesian models, you very often would put a distribution on your parameters. So if you know Bayesian analysis, the idea is that you take a random variable for your data. Let's say I'm very hand wavy, over broadly generalizing this, but you take your probability distribution, your likelihood here, then your parameter theta. You also put a distribution called a prior distribution. You have a P of theta. Okay. And the prior distribution is saying this theta is also a random variable. And instead of estimating it like maximum likelihood estimation, I would like to know a probability distribution, a posterior probability distribution. I want P of theta given the random variable X, which is my data. Given I've observed X, what's the probability distribution of theta? So it gives me not just a point estimate of theta, it gives me a whole probability distribution of theta given the observed data. And so I'm going to write some words down here. So that will be the posterior. That's kind of usually our goal. But we need to make theta random, so we need a prior distribution, and you Bayes rule to combine it with the likelihood to get this. This is a whirlwind Bayesian analysis. But the kind of the idea here is that now I've got a probability distribution, so I've got uncertainty. You can think of this as uncertainty of where is theta. It's not a here's the maximum likelihood point, it's just a number. I have a whole distribution. I can talk about some range of uncertainty in the estimate of theta. So yeah, so Fisher information comes up in Bayesian analysis for a thing we call Jeffreys prior. Again, named after a guy named Jeffrey. The Jeffreys prior says, I want to use what's called uninformative prior for my parameter. So uninformative prior means I don't make any assumptions about theta, except the following. It's not really an assumption, but it's a nice property to have. The only thing I want to say is that if I were to reparameterize my probability distribution in terms of something else, so I could reparameterize the Bernoulli instead of saying I want the probability theta, I could say parameterize it, write down that function and reparameterize it in terms of the square probability or the cosine of the probability, or just make up some function of theta and I reparameterize that as my parameter. Then I would like this prior distribution to mean the same thing. I want it to be parameterization independent, reparameterization invariant. And it turns out that the only way you can do this is by making your prior distribution proportional to the Fisher square root of the Fisher information. So if you wanted to have, you have a model with some discrete, like binaries, discrete random variables, and you wanted to estimate their probabilities in a Bayesian way, you can put a informative prior. I could put a prior between 0 to 1 for theta, make some distribution. There's something called a beta distribution people use sometimes. If you want some kind of bias towards, say, like less than 0.5 or more than 0.5, you can kind of model a prior to do something specific. But if you say, I don't want any prior assumptions, I want it to be completely uninformative, but I want it to be invariant to how I happen to parameterize this distribution, then the Jeffreys prior is the prior to use. Okay. So that's one application that I was going to mention about the Fisher information. This is not necessarily anything about a metric, although you can kind of phrase Bayesian inference in terms of geometry as well, under this metric of your parameter space, and you're trying to, again, talk about the posterior in terms of this underlying metric. That's one way to think of it. Okay. Another application, which is a really good one of the Fisher information, is something called the Cramer-Rao bound. Let me test any statisticians in the audience. Has anybody ever heard of Cramer-Rao bound? Okay, so maybe one person, one shy person has heard of it, but doesn't want to brag. Okay, good. So yeah, the Cramer-Rao bound, very famous if you're in statistics and estimation theory. So really, if you're in engineering and doing estimation theory, it also comes up quite a bit. Is the following: if you have a estimate, an unbiased estimate of a parameter. So if I'm trying to estimate my parameter, sorry, back here, this log likelihood of theta, and I want it to be unbiased. So my estimator, I'll call it theta hat. It's a statistic I compute from data. And remember, unbiased means that on average, this theta hat is equal to the true theta of the underlying distribution. Sorry about the camera again. So let's say theta is the true value. I'm seeing samples from, theta equals 0.7 or something. Okay, so that's the true theta. I want a function that estimates from that data what is the true answer, but from limited observations. That's my theta hat, and it's a random variable depending on the data I've seen. So that on average, I want to be equal to, that's unbiased. Okay, if you have an unbiased estimator, the Cramer-Rao bound says that, again, this is an uncertainty kind of property, is that the variance of your unbiased estimator is guaranteed to be bounded below by 1 over the Fisher information. Now, variance in an estimate is bad in general. You want, large variance is bad. You want precision in your estimate. You want it to be as little variance as possible. That's kind of the uncertainty in what you're estimating is the variance, right? You also want it to be unbiased because you want to be centered, that variance to be centered at the correct answer, and you're just somewhere to the left or right of the correct answer. But you can't, the point is that you can work as hard as you want on different ways to estimate some property, but you can never beat this variance bound if you want to stay unbiased. So if you design an estimator and you can kind of figure out the variance, if you've hit this Fisher information, you've done as best as you can, so you don't need to work any harder. So anyway, this is another nice application of the Fisher information, but again, this has nothing particularly to do with the geometry, Riemannian geometry we're talking about. Okay, right. The last thing I'll say is that the one application we're going to see of Fisher information in terms of Riemannian geometry is through what's called the natural gradient, which I kind of gave a real quick prelude to, if you will, last week. And the natural gradient is, very simply speaking, it's just the gradient of the likelihood, or sorry, gradient of anything really, under this Fisher information as a Riemannian metric. Remember, the Riemannian metric defines what the gradient is. And natural gradient is to if you're doing gradient descent of your likelihood, your log likelihood, instead of using a Euclidean gradient, you use the Fisher information as the Riemannian metric. And it turns out that will converge faster than, generally speaking, than the Euclidean gradient. And we'll go over that in more detail, but that's the other application I have. Okay, any other questions at the moment? I'll do also the Gaussian here. And what we'll see is a little bit about the again the intuition for what the Fisher information metric is telling us. And I think that's all I'll have time for. I'll have to do the natural gradient on Thursday to finish, I believe. Okay, so yeah, let's do a Gaussian or normal distribution. Because this is just a 1D parameter, and so it's not a very interesting manifold. Anytime you have a one-dimensional manifold, it's going to be just a curved segment or curve or line rather, and it's just kind of how fast you move on the line. That's really all you can do with Riemannian manifold with a one-dimensional space. Now a Gaussian distribution, we've got two parameters. The random variable, again, we'll use x is a mean and a sigma squared. And so I'm going to write in a previous notation, our theta here is equal to the vector mu sigma squared. So it's a 2D space. And remember, just to remind everyone what we did to introduce this last week is that we know the mean can be any real number. And we know sigma squared has to be a non-negative, or I should say, sorry, strictly positive number. So that's r greater than 0. That just means all the real numbers greater than 0. Okay. And so if we look at this theta space, this mu sigma squared space, as we said, we're in the upper half plane of R2. So sigma squared is the vertical, mu is the horizontal axis, and we can only be up here in the top half. We can't be, can't be below 0 for sigma squared. Okay. And so, yeah, so this 2D, I mean, what we would generally say when we draw it is looks like a nice flat space. If we put the Fisher information as a 2D metric, so a 2x2 matrix, every point in mu sigma squared parameter space, we end up with hyperbolic geometry, which is negatively curved space. It's the same space that Aman mentioned for embedding in hyperbolic geometry. It comes up again in the natural metric over the parameter space of Gaussians. Okay, and just to maybe put a finer point on it, every point in this space, just be clear, is a pair mu sigma squared. It represents a probability distribution, right? So this is, a Gaussian distribution. This point represents PDF, which is a Gaussian at a particular mu and a particular variance sigma squared. It's over here. I'd say a smaller variance. I'd have a Gaussian that looks like that. This point represents that guy, and so forth and so on. And every Gaussian you want is somewhere as a point in this space. And so the goal is I want a more natural metric where I can talk about distances between distributions under that metric. Okay. Right. So let me now talk about Fisher information in multivariate cases. It's really the same. You can write it a couple of different ways again. And it's the same kind of math we did before there. with the d theta, if you write that as a gradient, you just have to take care to think about it as a vector and not a number. And so when I talked about this being the expected value of the score function squared, right? Well, if this is a vector, what do I mean by vector squared? Okay, I'm going to write it in gradient notation so it's clear it's a vector. But what I mean by squared, and you can work, I'm not going to do this all over again, the crunching the equations again, but if you go back and do that whole argument we did with the equations before, you'll see that what I get is I get the gradient squared means the gradient times the gradient transpose. Okay, maybe I can take. I probably don't need all these brackets, but you get the idea. So this is a vector times a vector transpose. So in the case of two-dimensional theta vector, this is a 2D vector times a 2D vector transpose. And so you'll notice this is whatever my dimension is, in this case 2, it's a D by D matrix. So there's a 2 by 2 matrix inside of here that I'm doing. And that's what I need for this to be a metric, an information metric, is I need it to be a 2 by 2 matrix. And it's also the case that this is positive definite always. So I also need that, of course, but you can show that this turns out to always be positive definite. We saw that Bernoulli was positive definite 1 by 1 matrix, but more generally, if I do this for higher dimensions, I always get a positive definite thing. Okay. We can also write the Fisher information with the, just like in the previous case, with the second derivative instead of the first derivative of the law of likelihood. And there, let's see what notation we can do. It's still negative of the second derivative is what we had before. I'll just write the previous thing we had before was this. But what do we mean, of course, in 1D, this is just a number, the second derivative. But in multivariate cases, when I take a second derivative of a vector valued function or vector parameter, a multivariate function, I get a matrix called the Hessian matrix. So it's the second derivative of all the matrix of all the second partial derivatives. Okay, so this is going to look like it's a Hessian of L of theta. Okay, and the Hessian of L theta is going to be the matrix. I'll just write over here that Hij is equal to the partial derivative with respect to theta I theta j of in this case L of theta. Okay, so the Hessian matrix is just the ijth entry is the ijth partial derivative of L of theta. Notice it's symmetric. We know the Hessian symmetric. If you flip partial derivative orders, you get the same thing. So this is a symmetric matrix. It's a little bit harder to argue, but you can that when you're talking about a log likelihood and you don't have, you assume there's no degeneracies, and like if you change the parameter, it actually changes the distribution. And if that's the case, in any direction, and if that's the case, then you get that this is also a positive definite matrix. Okay. So yeah, so this is the Fisher information for a multivariate distribution. And now let's look at back at the Gaussian. Let me come over here. I only have a few more minutes. I want to get this finished. Let's work out just generally speaking, what we're doing here for the Gaussian. So for the Gaussian, everyone knows, I'll write this as this full theta that I've got 1/√2 pi sigma times exponential like so. Gives you standard PDF of the Gaussian. Let's just work out. I think what I'll do. The 1 term, and so let me call this is theta 1, mu theta 1, sigma squared is theta 2. So the 1 entry of this matrix, right, is going to be the expected value of the just second derivative with respect to mu, right, of the log likelihood, log PDF here, which if you take the log of this thing, right, this becomes a log term, it cancels the exponential in the second term. The first term won't have any mu's in it, only the second term will, so we only care about this term. Oh, sorry, this is a negative. So really just getting the second derivative with respect to mu of this stuff in here. But this is pull the minus out and just say 1/2 x minus mu squared sigma squared like so. Okay. This, if you notice, I can just pull the sigma squared out. Okay, if you take the derivative of this twice, this top term here, you're just going to get, again, with respect to mu, you're just going to get that this thing evaluates to a constant in mu. The second derivative of this kind of mu squared term becomes constant, and so I get just a constant. Okay, and in the end, if you work all that out, you're going to get that this whole thing becomes 1/sigma squared. Okay. And then if I'm out of time, let me just say that the answer for the rest of the matrix, the 1,2 term is because of symmetry, also the 2,1 term. You can kind of do these if you're interested, but those turn out to be 0. Oh, sorry, on the edge of the camera. Over here. And if you do the remaining term, which is the 2,2 term, the other diagonal term. So now I'm doing the second derivative with respect to sigma squared. This gives you 2/sigma squared. Okay, so the final Fisher information is 1/sigma squared, 0, 0, 2/sigma squared. And this is your metric. Notice it doesn't matter where I am in mu. I have the same metric. It only matters the height where I am in sigma squared. And so this is your Riemannian metric you're going to do if you do homework problem number 2. And I mentioned this last time, but it's in the homework problem. I already tell you what the geodesics are. And what we're asking you to do is compute the Christoffel symbols and just verify that the geodesics I gave you in the equations I gave you are actual geodesics. They satisfy the geodesic equation. But the geodesics look like these sort of circular arcs. They actually become elliptical because of this scaling by 2 in the vertical dimension. But they are not traveling at constant Euclidean speed as we think of in the plane. They're like a rotation in hyperbolic space, which is a hyperbolic cosine, hyperbolic sine kind of thing. And so they slow down, kind of like the Bernoulli example also, as they get close to a boundary, they slow down exponentially and like asymptotically never get to the sigma squared equals 0. It's an invalid point. And then if you have a geodesic, which at a point just starts with the velocity going completely vertical, either up or down, then the geodesic is a straight line. But again, not moving at constant Euclidean speed, moving at constant speed under this metric means exponentially slowing down this way and exponentially speeding up that way. So the speed, if you drew it as a function of kind of the speed, would look like the exponential function, which again is in the equation, is just the exponential function for sigma squared. And so again, never gets to sigma squared equals 0. It goes off to infinity, but this horizon is kind of at infinity. You can't ever reach it. And these are kind of geodesics that you get in this space. Okay, so that gives you everything you need to do that part. All right, thanks everybody.